I will now construct the sine graph. The equation for it is y equals the sine of the angle. Y equals sine theta. The graph is constructed by drawing a series of points. Points whose coordinates satisfy the sine equation. This axis will be called the theta axis instead of x. And this axis will be called the y-axis. These intervals, which I have marked off, will be 180 degrees, 360 degrees, and this one would be 540 degrees. And so on to the right. To the left, this scale is negative 180 degrees, this one minus 360 degrees, and so on towards the left. On the vertical scale, this will be the unit 1, this one the unit 2. Down below, this would be minus 1 and minus 2, and so on. I'm going to divide the scale up into smaller intervals. If this is 90, which is half the distance between 0 and 180, and I divide this into 3 parts, approximately, then each of these marks represent 30 degrees from the origin. So there you have 30, 60, 90. Dividing this into 3s again approximately. This would be 220. This would be 150, 180. Halfway between 180 and 360 is 270 degrees. And then this is divided into thirds, and this is divided into thirds, and so on. I don't want to put all the numbers for each of those marks because it simply clutters up the graph, and the details of what we want to investigate would be lost. We have the same situation over towards the left. This is minus 90, and we can divide that into thirds. That'd be minus 30, minus 60, minus 90, and so on. This middle mark between minus 360 and minus 180 would be minus 270, and so on. Now, what you will have to do is use your calculator and construct a table of values for each of these points. It will take quite a bit of time to construct that table. This is the row for theta, and this is the row for y. So using the calculator and calculating for sine of 0 degrees to start with, 30 degrees next, 60 degrees, 90 degrees, 120, 150, 180, 240, 270, 300, 330, 360, and that's as far as we'll go. If theta is 0, y equals sine theta, and sine theta, sine 0 I meant to say, is equal to 0. So we have then the point represented by that pair of coordinates right here at the origin. Taking the calculator and working out the value of the sine of 30, the number is 0.5, and so 30, 0.5 is located there. Let us now complete the table. For 60 degrees, y equals sine 60 degrees, and y is equal to 0.866, almost 0.87 approximately. That the sine of 90 is equal to 1. For 120, you will find it equal to 0.87. For 150, it equals to 0.5. Soon you realize that you're following some kind of pattern. And careful with sine 210, check your calculator. and you find that it is equal to negative 0.5. For 240, it's negative 0.87. For 270, it's negative 1. For 300, it's negative 0.87. For 330, it's negative 0.5. And finally, for 360, it is 0 again. For 60 degrees, 0.87. 0.87 is at 90 degrees, which is this mark on the scale. It is 1. Then for 120 degrees, it's 0.87, so it's even with this point. For 150, it's even with this point, 0.5. And here it is back to 0 again. 210, it's 0.5, which is located there. Then for 240, it's negative 0.87, almost up to 0.9, just above like that. Then at 270, it is negative 1. And then back to negative 0.87 for another 30 degrees. For another 30 degrees, it's there at negative 0.5. And finally, here it is at 0 again. Now, if you follow the dots, you can see that it traces out a curve. And so let's do that. Goes up like that, comes down. What we're doing are filling in the dots for angles in between that we did not calculate for. Comes down here through that, goes through here, and that's basically what the curve looks like. The curve will repeat itself in the way that the first part of it was drawn. So I'm just going to indicate that by drawing a little bit of the next cycle of numbers and quitting here. Similarly, you will find that if you draw the curve in the left direction using negative 30, negative 60, negative 90, negative 120, negative 150, and so on, that it will trace a path similar to the other, what I have on the other side of the axis. Come through here, this, peak at 270, negative 270, and so on. And I won't draw the rest of the curve for that. This graph will continue in this sort of up and down motion in a periodic sense for all measures of angles going to the right to infinity, and similarly to the left to negative infinity. This is called the sine graph. We refer to this kind of graph, because of this up and down motion, as sinusoidal. I'm going to use the same graph, but this time I will work on the cosine graph. Its equation is y equals cos theta. Use the calculator to determine the values of cos 0, then cos 30, then cos 60, and so on. You will find that the cos of 0 is equal to 1. The cos of 30 is equal to 0.87. The cos of 60 is equal to 0.5, and the cos of 90 is 0. Then we end up working on cos 120, getting minus 0.5, then minus 0.87, minus 1, minus 0.87, minus 0.5, 0, 0.5, 0.87, and 1. And we'll stop there. Plotting the points represented by these coordinates, 0, 1 is over here through that point on the y-axis. 0.87 is slightly below that, near 0.9. Then 60, 0.5, that's halfway up this unit scale. There's 0.5, and at 90 it is 0. Then it's negative 0.5, then negative 0.87, and finally negative 1. Coming back now, negative 0.87, negative 0.5, and at 270 it's 0. It goes up and up to 0.87 and finally 1. And if you continued with this, you'd find it starting to come down in the same kind of pattern. If you draw a curve through these points, you get a curve that is again sinusoidal. It's shaped somewhat similar to the sine curve, but it is displaced by an amount which we refer to as 90 degrees. It's 90 degrees out of phase, as it's referred to. And so the same thing will happen on this side, goes down like that, and carries on in this up and down sinusoidal motion. And so the green curve, which is also sinusoidal, as I've said, is the graph of y equals cos theta, and it goes up and down like this to infinity to the right and negative infinity to the left. The last graph we will study is the tangent, which is y equals the tan of theta. We're only going to sketch this graph and not spend time setting up the table of values for it. Let's make this 180 degrees, 270 degrees, and 360 degrees. Similarly, a similar distance to the left here. What we want to do is draw vertical lines through 180 and 360. The tangent function comes through the origin like this and comes towards the vertical line asymptotically and continues like this to infinity without crossing over the asymptote. Similarly, this graph comes down this way and reacts in the same way to this other asymptote. Similarly, between these two asymptotes, the curve repeats itself and continues to repeat itself like that to infinity to the right and to infinity to the left. The next topic is on special angles whose trig values the student should know without using a calculator. Of the functional values are irrational numbers, and in some cases it is best to leave the irrational number as a symbol rather than as a decimal. The special angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. For the sine of 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, use the sine curve to establish the functional values for those angles. Simply make a quick sketch of the sine function, noticing where the major points of the curve are, and I have shown that by placing heavy dots along the x-axis, that here you have 0, here we have 90 degrees, here we have 180 degrees, here we have 270 degrees, and here we have 360 degrees. You can see that for the sine of 0, the answer is 0. For the sine of 90, the answer is 1. For the sine of 180, the answer is again 0. For the sine of 270, the answer is minus 1. And finally, for the sine of 360, the answer is 0. And so here we have them. Similarly for cosine, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Draw a quick sketch of the cosine graph. Starts up here at 1, comes down like this, comes back up like this, and ends over here. We have 0 there. We have 90 degrees there. We have 180 degrees there. We have 270 degrees there. And we have 360 degrees there. This is positive 1, and this is the minimum, which is equal to negative 1. You can see that the cos of 0 is 1. For 90 it's 0. For 180 it's minus 1. For 270 it's 0. And for 360 it's plus 1 again. And so 1, 0, minus 1, 0, and plus 1 should be. And finally, for the tangent of 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, the quick sketch of this curve will establish those values quite easily. You have asymptotes coming down here at 90 degrees and at 270 degrees. The tangent curve comes down like that. Then it comes down through 180, which is located there, in this manner. And for 360, the graph comes down like this. You can see, therefore, that for tan 0, the answer is 0. Tan of 90, it's undefined. For the tan of 180, it's 0. For the tan of 270, it's undefined. And finally, for the tan of 360, it's 0 again. The quick sketch of each of these curves establishes the required quantities. A 30, 60, 90 degree triangle is drawn. This is 60 degrees and this is 30 degrees. We look at this triangle and think of it as part of another triangle, which I will now complete. Where all sides are equal is an equilateral or equiangular triangle. Let us assume that the length of the sides are equal to 2. So this is of length 2. This is of length 1, but of course this part is of length 1 as well, making it a total of 2, and this is of length 2. That establishes 60 degrees in each of the angles of the entire figure. This vertical line, making this a right angle triangle in black, makes this angle here equal to 30. Under those circumstances, if the right angle triangle, the black one, is looked at or concentrated on, using the Pythagorean theorem, the length of the vertical is the square root of 3. Using the definitions for the primary functions of a right angle triangle, which I have done earlier in this lecture, the sine of 30 degrees, this one up here, is the opposite over the hypotenuse, which is 1 over 2, or 0.5. The cosine of 30 degrees the adjacent side over the hypotenuse, which is equal to the square root of 3 divided by 2. And the tangent of 30 degrees is equal to the opposite side to 30 degrees, which is 1 over root 3. We won't rationalize the denominator here because this is how we learn how to deal with the calculation of the tan of 30 degrees without using a calculator, and it's best remembered by following the definition for the tangent, or any trig function for that matter, where the radical is in the denominator. That takes care of 30 degrees. To continue, let's look at the sine of 60 degrees, the cosine of 60 degrees, and the tangent of 60 degrees. Sine of 60 is opposite over the hypotenuse, and so that's the square root of 3 divided by 2. The cosine of 60 is 1 over 2, or a half, or I should say 0.5. And finally, the tan of 60 degrees is the square root of 3 over 1, or simply the square root of 3. Now, for 45 degrees, what we draw is an isosceles right-angle triangle. Isosceles right-angle triangle makes the length here and here each equal to each other, and let them equal 1. From the Pythagorean theorem, the hypotenuse is therefore equal to the square root of 2. That's the length of the hypotenuse. Having constructed the triangle this way, that makes each of the base angles here, so this one's 45 and so is that one. Determining then the sine of 45 degrees and the cos of 45 degrees, and finally the tangent of 45 degrees, using the definition for the primary ratios in a right-angle triangle, we have that the sine of 45 is the opposite over the hypotenuse, 1 over the square root of 2. The cosine of 45 is the adjacent side over the hypotenuse, which is therefore also equal to 1 over the square root of 2. And the tangent of 45 is 1 over 1. This you should remember. The tan of 45 is 1. I'll rewrite it here and emphasize that fact. The tan of 45 degrees is equal to 1. The next topic is inverse trig functions. If y equals the sine of x, the inverse to this equation is, exchange the y and x variable, and x is equal to the sine of y. Now y must be the subject of the equation. Therefore, we write that y is equal to the inverse sine of x. Y is equal to the inverse sine of x. That's what the -1 means in the statement. Don't look at that -1 as an exponent. There is another way to write the same idea, and it is by writing y equals the arc sine of x. Your calculator will have inverse function keys for each of the primary trig functions, sine, cosine, and tangent, but not for the reciprocal ones. You will have to determine the other reciprocal functions on your own through primary function results. Similarly, then, we have the same kind of equation written for the inverse cosine and the inverse tangent, and they are y equals the arc cos of x, or the inverse cos of x written that way. And finally, y equals the arc tan of x, or the inverse tan of x, written this way. This allows you to find the measure of the angle when you're given the ratio that that function equals. We'll now draw the graph of the inverse sine, cosine, and tangent functions. The sine curve is sinusoidal, and it goes up and down in this fashion. The inverse graph to this curve can be determined by drawing a 45-degree line through the origin and having it act as a mirror, where the line I have drawn is reflected through it. And the picture, or the apparent image you see on the other side, is the inverse function. And it goes something like this. And of course it continues down like this. In other words, the sine curve is drawn up along the y-axis, and it's similar in shape to the sine function drawn along the y-axis. Number of angles for a given number or functional value, let's say 0.5, then the number of times a line drawn through 0.5 and extended vertically cuts through the curve is an infinite number of times that it will do this. So for any given functional value, there's an infinite set of angles which satisfy that quantity. In other words, the sine of 30 degrees is 1 over 2. But so is the sine of 150 degrees, 210 degrees, 240 degrees, and so on. And so in the positive direction, you'll see that sine 30 degrees equals 1/2, sine 150 degrees equals 1/2, making complete revolutions of the angle in the Cartesian plane. We have sine 390 degrees equals 1/2, the sine of 360, that'll be 510 degrees equals 1/2, and so on and so on. Also in the opposite direction, for negative angles, the sine of negative 210 degrees equals 1/2, and so on for negative angles. You can see then that we have an infinite set of possibilities for the arc sine of that number. The graph illustrates this as well. Through all the points, the vertical line cuts the curve is the solution for the arc sine of 1/2. So what we have to deal with here, since we in most cases require only one solution for the arc sine equal to 1/2, we deal with what is referred to as the principal part of the curve.